Well, thanks for the opportunity to talk. Hopefully this engenders some fruitful discussions. I haven't had the chance to talk with sort of the swampland community so much about this, but I think there's a few interesting results coming more from the bottom-up amplitudes constraint side that make contact with some things familiar to the swampland community. Um, so the basic question motivating this is, as you guys are interested in knowing, how the low energy couplings are constrained by consistency in the UV. Okay, not just in the naive Wilsonian way, but what are the more subtle constraints on infrared couplings when you demand good UV behavior, for example, boundedness at high energy, the amplitudes, which we'll discuss in a bit, unitarity in the UV. And there's been a great deal of recent work on constraining low energy couplings, for example, using dispersive representations, which when you use Reggie boundedness of an amplitude, you can relate the high energy behavior of the amplitude to the infrared behavior. And ultraviolet unitarity then furnishes some rules for you on the low energy couplings. So when you assume unitarity in the UV, you can get positivity constraints on low energy couplings. Okay, but there are obstructions to doing so, technical obstructions in the presence of graviton exchange. So the famous T-channel pole, for example, is an obstruction. So there's been progress recently using some rules at fixed impact parameter instead of expanding around the forward limit, the small t limit. And despite this, there are still divergences in 4D that this fixed impact parameter doesn't let you so easily get around. So alternatively, stuff you know very well, is trying to consider top-down constructions in string theory to reproduce some low energy scattering amplitudes that exhibit all the consistency conditions that we expect in the ultraviolet. Okay. And along the lines of a conference that I know a few of you were at in last May, so about a year ago almost to the day, where some swampland folks and EFT constraints and amplitudes folks were brought together to try to see if what kind of halfway place can be occupied, where you can bridge this gap between sort of rigid amplitudes point of view constraints on infrared couplings and a lot of the amazing facts that you guys have been learning from the stringy side. So today we just try to make some progress in that direction by considering a class of ansatzes for amplitudes and constraining them. Okay. So let's be even more concrete with a concrete goal, which we won't tackle in full today, but we'll do this for a couple amplitudes. And just, can you write down a weakly coupled amplitude for some standard model process, including gravity, which at high energies is consistent with Lorentz invariance, locality, causality, and unitarity. Okay, this is famously much more difficult than you might think at first. It's actually quite challenging just to write down a function which passes these basic checks, for a 2-to-2 process. Okay, and so today we'll motivate a class of amplitudes which are very familiar to string theorists, but it's nice to motivate them from the bottom-up sort of on-shell point of view. But what's surprising is that the constraints on these amplitudes are then surprisingly stringent. You might have expected that there'd be very few constraints from this point of view when you don't invoke the full machinery of worldsheet string theory, but that's not the case. They're actually, you can already notice fairly constraints just as a on-shell, low-energy person with unitarity at your disposal. And the workhorse that will be constraining the amplitudes is perturbative unitarity, in particular via having an imaginary part which is positively expandable in partial waves. Okay, so we'll discuss this in a bit, but as a quick summary of what's to come, we will just be writing down amplitudes which look very, very stringy. In some cases, they'll literally be, for example, the heterotic string amplitude for 4 gauge bosons, but where we let the gauge group and the gauge coupling vary. They're not fixed as they are in string theory from the worldsheet. Okay. So
can I ask a question? I'm sorry,
yeah.
just on the previous slide. I just want to understand what is hard. So the issue is that you want perturbative unitarity. That is what's hard. So like typically amplitudes grow with some power of S or something. But
Yeah,
you
well,
don't want it to
so
grow indefinitely. So you need some exponential suppression to come in or something like this, or
yeah, I mean, you don't need it to be exponentially bounded. In fact, on the
yeah.
next, I'll discuss on the next slide here. Let me just,
Okay. All right.
this
Well, thank
slide
you.
has a bit more beef. Yeah.
Okay. Thanks.
So, okay, so just if we're studying the S matrix, just the fact that the S matrix as an operator, so it should reflect Lorentz invariance and also whatever gauge or global symmetry invariance we're dealing with. Okay. And so, therefore, this operator should admit the following expansion. Okay. So this is general so far, but these are the polynomials which are just reflecting Lorentz invariance. So these are, for example, Legendre polynomials. They depend on the external states, which are captured by the helicities. We'll be talking about massless particles. So the helicities, this is the space-time dimension, D, and this would be the spin of the exchanged particle, J. Okay, so this reflects Lorentz invariance, these polynomials, and when we do concrete examples, we'll be clear about which polynomials are relevant. These are the analog for expandability, which is covariant with respect to the gauge or global symmetry group, where these are the external representations being exchanged. So each particle, helicity 1, representation 1, and then exchange representation R. You can capture them in terms of exchanges, even though we're not sitting on a pole yet, but this is a covariant way of expanding the S matrix. Once you expand in a way that reflects this symmetry, Lorentz invariance and gauge and global symmetry invariance, then just the statement, and I'll just doodle here just so it's a little more clear, just the statement that we have S is 1 plus IA, and then the fact that S dagger S equals 1, or really is less than or equal to 1 as an operator, then implies this positivity. When you expand this out in terms of A, okay, this is the non-perturbative constraint, which if you've seen, gives you this Argand circle, okay, where the imaginary part is greater than the mod square. And then there are two, we will be working at weak coupling, okay? So we want to work at weak coupling today. And then at weak coupling, there are two basic limits that are useful for us. So this is the high energy boundedness. This is the unitarity violation that as S becomes large, if the amplitude grows, if cross sections grow with energy, then at a certain point, we will violate this circled in red, okay? We're going to have ansatzes that manifest this condition that this is satisfied, okay? So we're going to just guarantee that that's satisfied. The exponential softness of string amplitudes does this for you, indeed, okay? You don't need exponential softness to obey this, but certainly that will do the trick. And this limit is the limit that will not be manifest and will furnish the constraints. But so we'll review an example in a second. For example, the nonlinear sigma model, just to see why it's not trivial to do this. It's not so hard, as we'll see in the case of something like the nonlinear sigma model. But what we will see is that it's very, very hard in the presence of gravity. And I'll explain why it's harder in the presence of gravity to write down even an answer that just satisfies these basic constraints. Okay. So let's just make some further assumptions on analytic behavior, which will be relevant to why this is constrained. Okay, so we already said the first one. So we need boundedness at fixed angle and high energy. Okay, now the next one's very important for making this difficult, and it's an important physical constraint. It's related to the physics of causality. So we want Reggie boundedness for complex S at fixed T. Okay, and so this is related to it goes back to the classical Kramer's Kronig, the forward limit being related to a large energy 2-point function, and the classic arguments that go back to Nima and friends in 2007, bounding the coefficient of the d phi to the fourth operator. You consider some scalar condensate, You could get superluminal propagation if you don't have the right sign of the d phi to the 4 coefficient, this irrelevant operator. These can also be framed in terms of the physics of Reggie-boundedness captures the same physics, this physics of causality. And
sorry.
So we will yes?
Sorry, can I ask a quick question? So you explained this related to causality. And I guess that even in a theory of gravity, I am entitled to impose strict causality very far away, right? That's why still a principle I want to impose. Because one could, imagine that maybe in gravity, like causality is not exact, maybe there's some non-perturbative G Newton stuff. I think that's the case at finite distances. I just wanted to confirm that
we want a perturbative, so we want a weakly coupled description right now where we can expand around. So yeah, I can't comment. Perhaps if you're imagining some highly sort of non-local regime, but yeah, I mean, I want to be able to capture weak coupling at long distances. I should be able to recover. I should have Reggie boundedness, in particular in the presence of graviton exchange. This S squared is graviton exchange. The power is smaller, not in the presence of graviton exchange, but.
All right, thanks.
Sorry, can I ask more about this Reggie boundedness? So it's not really the same as superluminality, right? It's
well, they're related.
They're not equivalent. They're not equivalent statements.
Not equivalent statements, but Reggie boundedness is related to the physics of causality, though. I mean, there are different bounds. There's a Poisson bound. There are these sort of classic.
Poisson bound, isn't that the bound on quantum field theory amplitudes? That is holding gravity.
Yes, it's a Poisson. Indeed. So we can't say, strictly speaking, it's a QFT. It's derived in the context of QFT. So there are subtleties here, but it's this is nonetheless.
Is there any kind of a proof, or is there any solid? I mean, I understand that I believe I believe in Reggie boundedness, but I don't know what is the status of it. There's no proof of it, or there is a proof of it? Or...
I think there's these recent works by Sasha Ciboedo.
Yes, Sasha Ciboedo recently. That's right.
He has shown this rigid boundedness, precisely because I think it's dominated by the gravitational semi-classical, right? Like the semi-classical.
Yeah, I mean, I read that paper, but it wasn't very easy to follow. I don't know if there was like really it was a collection of different possibilities, and then so Sasha claims that he has proven Reggie boundedness in any consistent theory, including gravity. Is that the?
I think for weakly coupled theories.
Okay, very good. Thanks. Yeah.
I should double check. I mean, I can double check, but yeah, I think this is, at least this is
as
far as I know, this is the most recent, or the status of the art regarding.
Yeah, I read the paper, but I didn't see a one line kind of claim like that. But I'll go back and look at it. Okay, thanks. Sorry. Carry on. Yeah.
No problem. Yeah, yeah, that's my understanding as well. That's the most up-to-date analysis of sort of more detailed constraints, Reggie boundedness. I'm not familiar with the exact assumptions though that go into it. Sorry, but the other condition we'll impose, that's certainly it's not a hard rule. You can try to deform away from it. People have studied this. With such, for example, amplitudes with accumulation points in the spectrum. But we won't be looking at that. We'll impose a fixed number of spins at a given mass. Okay. And so that means that a residue in S will be a polynomial in T. Okay. So, all right, we will not manifest, though, positive expandability of the imaginary part. Okay, so that's the one that will look non-trivial and interesting. Everything else will be made manifest. So let's just review how this works in the nonlinear sigma model. Okay, so Goldstone scattering at low energies in the nonlinear sigma model can be captured in the following way. All right, and it's easy to see that either exchanged SUN representation, singlet or adjoint, is going to grow with energy. Okay, we'll have some scalar partial wave which grows with energy. So this description starts violating as S is of order F squared, violating unitarity. Okay, we violate high energy boundedness, and we want to UV complete. Okay, so our rules will be that we can only add poles with positive M squared, the Reggie boundedness that we were just discussing, and positive expandability of the residues. Okay, so your first guess might be something very brutal. Let's just guarantee it's extremely soft at high energy. Okay, so let's use an exponential. Okay, we even have it's crossing symmetric, this factor, wonderful. And we could just multiply our original amplitude by this function. But this will very badly violate Reggie boundedness for complex S, right? For complex S, this will blow up. And so that's this basic tension. If you want to satisfy Reggie boundedness and then softness at fixed angle, this is difficult to do. Okay, so naive guesses will rarely do the job. So let's consider introducing a massive exchange. Okay, that's what would be more conventional. We're only growing with S, so we don't need something so brutal anyway. So this is a following guess, where now I'll comment that I've decomposed the traces into these projectors. So this would be a singlet, okay, and this would be the symmetric adjoint exchange. This is just teeing it up so that we can check unitarity in the basis from the second slide, or the third slide. Okay, so all right, so long as F squared, so long as these new UV states come in below the scale set by F squared, we're bounded. Okay, we're bounded high energy. That's great. But now in the context of this specific UV completion, we now have an imaginary part, right? This is the pole at S equals M squared. And then we have a positivity condition there. Okay, and so that constrains F squared greater than 0. Now, of course, if you have the full realization of this symmetry, you know that, of course, that just means, you know, we have e to the IF times SUN matrices. And yes, F had to be real so that F squared is positive. But keep in mind, we're doing this from the bottom up. And this will be relevant when we're trying to do this with these stringy amplitudes, and we're not going to be appealing to some worldsheet description. Okay, so the point here, the lesson to draw here is that once in the context of a specific UV completion, we generate constraints on the infrared. Okay. All right. So let's review. Now let's look at gravity. So we have the same problem for graviton exchange. All right, so if we have identical scalars interacting through graviton exchange, then we see that we're going to have the same growth of partial waves. Okay, so when S is of order of a Planck scale, we get the same breakdown of unitarity. And we can still seek a weakly coupled description. Okay, we don't have to give up on weak coupling, but this is harder. So let's look at why this is more challenging than the previous example. So the previous example was very easy, and that's because there was no pole yet. So the first amplitude had no imaginary parts, right? It was just a polynomial, and we got to introduce the first singularity, right? So this first singularity at S equals M squared, there's no condition a priori on the right. And we got to no trouble at all. Okay. And then we got that F squared was greater than 0. Okay. So why is graviton exchange different? Because it's already an exchange. Okay. So we already have this interaction at low energy. There are already poles whose imaginary parts we have to be consistent with. Okay. And any modification along these lines, okay, we have the pole we had originally, and then we put some new pole at M squared. So just by a residue theorem, it's mutually incompatible for these poles to have the right sign. Okay. So if we just introduce a bunch of poles, then some of them are going to have the wrong sign, okay? And so this motivates trying an infinite number of poles. If we have some infinite number of poles, then we can still hope that we can get away with this because the amplitude will blow up elsewhere at some non-physical kinematics. But for any finite number of poles, this will fail, okay? So we can't just proceed in the naive way, and it's because we already have massless poles that factorize consistently, and we can't deform that, okay? So that's what's difficult about gravity. All right. So let's just proceed from the bottom up, trying to derive an amplitude that will satisfy our constraints, trying with the sort of next most advanced deformation of what we tried in the nonlinear sigma model case. So let's just try our infinite number of poles, okay? We're doing a graviton amplitude. It's natural to have an ansatz, which, well, we don't even need to manifest the STU symmetry, but we'll start with a product ansatz. So we'll consider this infinity of poles, okay? So we have an infinite number of poles and then some numerator, okay? Now this is where it's relevant that we said we want a finite number of spins at a given mass level, okay? So this means that whenever we have a residue in S, okay, all the remaining poles in T and U need to be canceled by the numerator, okay? This guarantees that we won't have an infinite number of spins. We need a polynomial in T, okay? So every residue in S should be a polynomial in T and residues in T and U. So it's natural to then just have a product ansatz for the numerator, all right? And then we impose this condition. So we impose this cancellation condition. So for example, we have an S-channel residue at some MSI squared. And we have the following function left over, and we impose cancellation of all the poles downstairs. So the condition for cancellation of these poles is that the sum of S mass squareds and T mass squareds is in the set of U factors in the numerator, okay? These are UKs, plus the condition for the other two channels, okay? So then this most naive bottom-up approach furnished the following infinite product, okay? So following the infinite version of the nonlinear sigma model, just introducing a pole guess, furnishes this infinite product formula, which is a very famous function that everyone here knows. And that's essentially the Virasoro Shapiro amplitude, okay? So if we set alpha prime, introduce a new mass scale, this string scale, and we write it this way, and this function exhibits exponential softness at fixed angle and high energy. It's Reggie bounded. We can, if in the presence of gravity, we can add 2 more powers of S, okay, to be bounded by S squared. And then it manifests a field theory limit. So if we have some field theory amplitude, then we can dress it with this factor. And as alpha prime goes to 0, as we decouple these stringy states, we just recover our field theory amplitude, okay? So this is a lovely prefactor that we can use to try to unitarize our low energy amplitudes.
Sorry, can I ask something?
Yes.
In the previous, I mean, if it's from a previous slide, you said you cannot have a finite number of poles, otherwise you have the problem with the residues, or the sign of the residues, right? Is that sufficient to conclude that there is no consistent amplitude with gravity that will have a finite number of residues, or there could be some here?
Well, I mean, I would be interested to see something more rigorous. I mean, this was in the spirit of a motivation. You know, I'm using this finite number of poles. People look more rigorously. You know, for example, Cliff Chung and Grant Remen have been studying rigorously deformations of string amplitudes, not precisely from this point of view of looking at writing a finite number of poles down. I mean, I have not seen it done, but I also can't say I've seen a proof. I can't say, I don't want to say definitively, since I have not thought enough about it. If there are loopholes, if there's, oftentimes there's sort of strange little loopholes to these things. But it would be, it would be interesting to see a proof of it.
Okay, thank you.
Sure. Okay, so we're going to use this prefactor. And by the way, it's worth commenting. It shouldn't be surprising. So not only was this not a proof, it's certainly not the first iteration of using this as a way of motivating the Virasoro-Shapiro amplitude. This is a footnote from Virasoro's original paper, where he thanks a colleague for suggesting this way of also deriving the amplitude, writing infinite product formula and imposing cancellation of the double poles. All right. So if we took our scalar amplitude and we just dress it with this factor, so we followed this sort of simplest way of motivating a unitarization, we land on the 4 dilaton amplitude in type 2b. Okay, I'm writing it in 4 dimensions. All right, so we know that's unitary. We don't have to review that, but let's just see if we can add a chordic coupling. So this gamma string looks like a hammer, and let's see if everything is a nail.
Sorry, could I ask a question?
Yes.
About this prefactor. So
sure.
Is there a sense in which putting this prefactor is assuming something like that the states you're scattering are themselves string states? Closed string states in particular?
Well, certainly, yeah, it's so we know it's not, my sense of that is from string theory, so not, yeah.
I see.
Do you mean in some other more invariant way? We know that this prefactor comes out of, closed string theories, and, well, yeah, go ahead if you
just in particular, it's not something that you would expect to have for states that don't unify with the graviton in a closed string. For example, open string states.
Yeah, exactly. And in particular, if you do this for, it's, as you say, it's not unique either. I could use the sort of open string analog of this to unitarize my amplitude. So that's why this is just the motivation of how you can land on it from the bottom up. And I don't know a more invariant way of characterizing other than from, representation theory and string theory in the world, the sort of the things you're very familiar with, of saying this is the closed stringy.
But it is fair to say that kind of the assumption you're making is that the states you're scattering are themselves closed string states in some sense.
Yeah. Yes, I'm certainly, that's the point of view I'm adopting here. And I'll comment on the open stringy version at the end also of this game and why it's not as interesting. It'll be clear why I've picked this closed stringy version to talk about today.
Yeah, great. Thanks a lot.
Sure.
And one more question related following this. So does this mean that I should understand the bounds that you will talk about as valid only if they have a closed string interpretation? Like, for instance, if the U1 gauge field comes from closed strings and so on?
Well, yeah, I'd like to, this is something I'd like to get your guys' opinion more on, but certainly I would think that these bounds are bounds that basically the bounds say whatever, since we're not, the whole point is to obviate discussions of compactifications, whatever, and see if you can make sort of more invariant statements. But obviously they're not global statements about it, the whole string, the whole space of compactifications you could consider, but they're certainly, working backwards, they're statements about amplitudes that fall into the class that they're describing. Those amplitudes seem like they certainly are weakly coupled closed strings. Maybe there are other weakly coupled closed strings that could have warp factors or weirder amplitudes that I'd love, if anyone knows, I'd love to hear their point of view. But yes, these will be statements that, roughly speaking, they're statements about what weakly coupled closed string completions could look like. And weakly coupled open string completions or completions on branes or could look different. They'll have different amplitudes, and you'd have to consider those constraints on their own terms. Yeah.
Okay, good. Yeah, let's go on.
Okay, so, all right, so we can check unitarity at level 1 here. We just added a quartic coupling for the scalar. Okay, so we just added a 5/4. So this is just 5/4 theory with gravity. Okay, and you take the residue at level 1, you get a polynomial, a 4th degree polynomial in T, and you just expand in Legendre's, as I was saying. And these are the partial wave coefficients, and they have to be positive. Okay, and that just imposes this constraint. So in particular, let's say we decouple gravity by sending m Planck to infinity. That's not consistent. Okay? So the string scale cannot become arbitrarily low in Planck units here at some fixed lambda. Another way of saying this, you can't just unitarize 5/4 theory with no gravity using this sort of closed string completion. So kind of analogous to Jake's question, you know, this needs the graviton there to be useful. You can't, this is not going to be a unitary softening without gravity. And the way to detect that is with these unitarity constraints. Okay, but 5/4 theory is not all that interesting. It will be a lot more interesting to consider flavor and color. Now, and to do that, sort of the most technical point in all this work is this business with 6J coefficients for SUN and SON, or whatever group you want to consider. We consider SUN and SON here. And the basic point is that when you write down the amplitude in the most obvious way, so these projectors, for example, are things like, just so I can be explicit, you know, our favorite FABCs. For example, we call that the adjoint exchange in the S channel, as an example. And when we write our amplitude, we write them in terms of these projectors in the S channel, the T channel, the U channel, okay? But when we actually impose unitarity, all the color structures that are in the amplitude need to be re-expressed in terms of color structures in the channel in which we're taking the residue. So we need to re-expand the T channel and U channel FABC contractions in terms of S channel, okay? And so this is just a question of essentially expanding in a basis. And so we need to re-expand the T's in terms of the ones in the S channel. And then there's some sort of kernel that does this. And these are 6J coefficients. Okay, this is what 6Js are, okay, for a general group. And you can deduce what they are just by contraction. Okay, so you have to calculate these, and then there's some functions of Casimir's, you know, they're functions of n. Okay, and so these will appear, and they'll produce a lot of the sort of more non-trivial and surprising constraints. So let's just review a very simple example so we're clear. So for example, if we have the singlet, so if we have a global symmetry, we have fundamentals of SON, we just dress our 5/4 amplitude, now we make it some ON, some SON model. Okay, then the T channel and S channel singlet, we just compute this overlap, this factor, and it's 1 over the dimension of that fundamental. Okay, so this would produce factors of 1 over n. And this is how functions of n will appear in our positivity constraints, okay, by this re-expansion. If there are any questions about that, you know, good time to ask. Okay, so let's look at that. Let's look at exactly that example. And let's look at, instead of just Legendre's, which are the polynomials for 4D, we'll do the scalar polynomials for general space-time dimension. These are the Gegenbauers, just the d-dimensional Gegenbauer polynomials. So they're just the appropriate sort of generalization of these spherical harmonics. Okay, so this is our ON dressed scalar amplitude. Okay, so as I said before, we do this re-expansion, and that's where these 1 over n's come from, or 1 over the dimension. All right. Okay, and so the spin 2 partial wave that we exchange just at the first mass level, that's where the most interesting constraint comes from in this case, is just mass level 1. Okay, that yields the following constraint. So this is a bound on the dimension of the fundamental. So if you try to have a global symmetry on these scalars interacting gravitationally, you can't have too much global symmetry. Okay, so we don't see that you can have no global symmetry, but the amplitude already doesn't like too much of it. So in particular, in 4D, you can't have some SO8 using this. So you can't have these scalars exchanging, interacting by SO8 multiplets. Okay, so that's no good. Okay, so let's move on to the gauge boson ansatz. All right. So we land on essentially the heterotic string amplitude. We put in blue these sort of heterotic factors since you don't strictly need them. They produce stronger constraints if you leave them out, so we won't present them. But just as more of a bottom-up comment, well, I'll say on the next slide, but so you can't add, because of Reggie-moundedness, we can't just add polynomial terms here. Because we already have these helicity factors out front, which go as s squared. Okay, and so this is actually pretty rigid, this formula. We can't deform it. And indeed, you might think we could add more sort of 1 plus alpha s. Oh, let's do 2 plus alpha s, alpha prime s, or 3 plus alpha prime s. Let's just keep softening it that way. Okay. Well, you actually can't do that either. And that's because the only reason we can even have those factors is that consistent with our polynomial residue nest being a polynomial in T statement, is that every residue has this factor. Okay, so every residue has a 1 plus alpha prime T, a 1 plus alpha prime U. But they don't all have 2 plus alpha prime T, 3 plus alpha prime T. And we'd have an infinite number of spins at mass level 1 if we started adding these terms. So this is a rather robust ansatz. It's really not easy to deform it. And so, you know, it's not just merely copying the heterotic string amplitude from the textbook. You know, the rigidity is well motivated from the bottom up as well. Okay, so let's study.
I'm sorry, I know there's not too much time. Like even in the scalar case, like if when you write an amplitude form like this, how should I understand this? Like, are these gauge fields exchanging?
Yeah, these are good. This is, I mean, literally, I'll show the constraints on the next slide, and then I'll tell you. I mean, this is a guess, if you like, for the 4 gluon amplitude at high energy. I mean, this is just a guess. Like we technically, you know, you could say we don't know. Maybe this is what the 4 gluon amplitude looks like.
But do you have a connection to, like, is this an exchange? Is this coming from exchanging the 4 gauge fields, exchanging something in the middle, or?
Yeah, this is 4. Okay, so this is 4 gluons.
Yeah.
Okay.
And what goes on in the
this
middle?
part, this is everything in the brackets here. We
Yeah.
know. I mean, you just calculate this in field theory. This is the non-abelian.
But that's just a pure gauge theory.
With gravity. I mean, this is the gauge boson contracting with gravity.
And if I add some charged matter to this, and now I
mean, get other terms too. You could do that, yeah.
And how does that affect this analysis then? Like, are you bounding here? I'm trying to understand, is this a general theory involving a gauge field, or is this just pure Yang-Mills coupled to gravity that you're bounding?
This right now is pure Yang-Mills coupled to gravity. I did not look at coupling to charged matter. We could look at that too. I don't have an intuition off the top of my head for if that will spoil things or just add more parameters.
I see.
But the point right now, what we're constraining is that I have G Yang-Mills squared, and in particular, I'm only constraining dimensionless things. So the dimensionless thing is G Yang-Mills squared, you know, G Newton over M string squared, or G Newton M string squared.
So like previously you looked at like pure scalar 5 to the 4 or something, and now you're looking at pure Yang-Mills.
Now I'm looking at pure Yang-Mills coupled to gravity, and I'm letting the things I'm letting vary. The only parameters I can vary are the gauge coupling. Yeah.
Okay. All right.
Really, the gauge coupling times the ratio of the Planck scale and the string scale, and the n. I'm going to look at the rank, the n of the SUN or SON. those are the only two things I've allowed myself to vary.
Right.
And I've tried to motivate why that's actually not insane. I mean, not totally random. I mean, the structure is pretty rigid. And but
Right,
those
but
are the two things.
I see, I understand. Yeah.
Yeah.
Okay, thanks.
So indeed, let's just look at so in D equals 4, these are the constraints you get. So let's just look at this. So this orange one is the one without heterotic poles. And you know, it's not, we don't really need to look at it. I just did it since it was an obvious way to kill it as an ansatz, but it's more constrained, and so there's no point really to think about it. So the version which is really the heterotic amplitude are the blue regions. Okay, so we have SO48 is the corner here, and SU25. Okay, so in both cases the rank is 24. Okay, and that occurs at this value of the coupling. G Yang mill squared is twice the string scale squared over the Planck scale squared, and that's the coupling fixed by the heterotic string. Okay, so the coupling can't be any bigger than that, the Yang-Mills coupling. So this region is disallowed, you know, over here. Okay, so there's a max value on the coupling. And there's also the constraint, which is a function of the coupling and the rank, and it produces this bounded region. Okay, so there's this bound on global symmetry. So kind of back to questions from before, if you have whatever convectification you consider, if this is what your 4-gluon amplitude looks like, then perturbative unitarity is going to tell you this is what n, this is how big n and the coupling can be. Okay, so it's worth, so this is where the constraints come from, right? Every constraint comes from some state that would become a ghost, some exchange state that would become a ghost if you violated it. It would be a negative norm state, okay? So the states are scalars at mass level 1, and this is a general thing we'll see. They're always the most subleading Regge trajectory. So they're always scalars. So sort of zero impact parameter amplitudes. In this case, the one that produces the bound on the coupling, the sort of hard bound on the coupling, is this Young tableau for SON. It's the largest dimensional representation that is exchanged between the adjoints. And it's a kind of a funky, you know, I haven't seen this kind of representation show up. And the other one is the scalar. So this is a singlet, the singlet of SON. Now it's the same in SUN. It's the biggest representation that could be exchanged, highly symmetric in the indices. And then also the scalar that does it. And in fact, you can derive this generalization. This can just be derived for Lie algebra with the FABCs in terms of the adjoint Casimir and the dimension of the adjoint. Okay, so if you have an amplitude, which is the structure of the ansatz from before with the FABCs, Kronecker deltas, so graviton and sort of gluon exchange, then it seems like these are the constraints you get. This is a conjecture, I don't know. It comes from this biggest representation. I don't know off the top of my head the invariant way to characterize that and see if that's a bound you'll always get. But this one, the second one, is derivable pretty simply. Okay. So this would be sort of a fun conjecture. Is this always the case? So it's worth commenting. So the bound on the coupling is an anti-weak gravity bound, right? So it says that the string scale cannot get too low in the context of this completion. Okay. Sort of complementary way of saying that, since it's a dimensionless statement, is that we're using gravity to unitarize our amplitudes, so we can't overwhelm it with a gauge coupling that's too strong. Okay, so sort of pure gravity will always be fine in this class of ansatzes, and so you can't make the gauge part too strong, relatively speaking. Okay, and so the title of this had the standard model, so we better make at least a couple of comments on the standard model. So we can just plug this in for example.
Sorry, just a quick question about this.
Yeah. Yes.
does this really have anything to do with unitarity, or is you demanding perturbative theory? So isn't this just a statement that if this wasn't the case, the theory wouldn't be perturbative at the
Well, you can always say yeah, but that's
highest-
always what we're doing. But I mean, this is motivated by saying, I mean, well, you don't have to give up. I mean, there's the famous Lee, Quigg, and Thacker paper looking at longitudinal W scattering. Let's say, let's not give up on. I mean, you could say it's things like Technicolor. It's strongly coupled.
If I just demanded perturbativity at
yeah, this is saying this is
blank,
only
isn't
legit
this-
for perturbative. Yes, this is assuming a perturbative analysis. But if you grant that, then these are the constraints that you seem to land on.
Yeah, I'm just trying to understand, does it follow from unitarity or just purely demanding perturbativity? Or
Well, it's perturbative unitarity. I mean, you have to.
yeah, but so it does need unitarity as well, you're saying?
It's unit. It's certainly a statement about unitary. Yeah.
Okay, all right, thanks. Sorry, John.
So if we put, for example, gut scale couplings for SU2 and SU3 gauge bosons, then this is the bound you'd get on the string scale and the Planck scale. And so this is the sort of reduced. This is the M Planck that's of order 10 to the 18 GeV. And so that would be this bound, the bound you find on the string scale, which is reminiscent often of the attempts to bring down the string scale in the context of heterotic string theory is difficult, and often lands in the neighborhood of 10 to the 17 GeV. Basically, as weakly coupled as these gauge bosons are, is how far you can bring down the string scale. Okay, and then if we shut off the Yang-Mills coupling altogether, you get statements about global symmetries. Okay, global symmetries, constraints on SUN. Okay. So now let's look at general dimension constraints. And so I just have to issue sort of a final a caveat here, which is that these are not strictly necessary because we do not do the full spinning analysis using the full structure of the f to the 4 tensor that has to appear in front of amplitudes for particles with spin in general dimensions. But they're nonetheless sufficient conditions for positivity, and the strongest constraints in 4D came from the configurations of the amplitudes where the polynomials are Legendre polynomials. They actually are the scalar polynomials. So perhaps it's well motivated that these will be the true constraints when you do the full responsible analysis. But nonetheless, so these are sufficient but not necessary conditions for unitarity of these amplitudes. Okay, so if we just the point is just redo the analysis in 4D now. So use in 10D. And this is what you find. So we get the same bound on the coupling. So which is exactly the value fixed by the heterotic string. And n, so n has to be less than 32 plus 16 over 19. So the largest n allowed is SO32. So the SO32 heterotic string is up in the corner there. Okay, so that was pretty surprising. So perhaps the most interesting plot is that what we can do is fix the coupling. So we fix G Yang-Mills squared at the max value, right? This max value set by this line. So that's 2, so that's 16 pi G over alpha prime. So we fix it there. And then we vary the space-time dimension and the rank, okay? And then this is the plot, the constraints you get. So this R is 26 minus D is this, which you all know much better than I do, this bound motivated by swampland constraints. And then this upper bounding curve is just deriving the constraints as functions analytically in R and D. at this max value of the coupling and then plotting it. So what's interesting is the bound is identical for these first two sections for SON and for SUN. Okay, so they're identical bounds. Then in this corner in the vicinity of 10D, they actually become different functions. So they separate. SON is this outer one. They separate, but they, in all integer dimension, they meet again. So from this point of view, it's unclear why something so invariant is going on. And I'll explain on the next slides why it's really surprising. So for the partial wave coefficients, you can derive these conditions. So this is just the analog.
Can I ask something before you move on? It's very nice to see how you recover the bound in the rank, but I have a question that I would really like to know your opinion. Like, we know that this bound only is not general, like we know that only works in string theory compactifications when you have, for instance, 16 supercharges. No, that was what was proposed.
Right, right.
And here you're not assuming supersymmetry, but somehow the assumption must be there. And I can see two places where it can be, and I would like to know which one you think it's more likely, or I don't know, which one is more important. One is the when we were discussing the answer that you put the closed string behavior, because maybe that suggests that it's a bound related to weak coupling, like to have a worthy description and so on. And the other one is that, okay, maybe it's valid beyond that, but still, as Aaron was asking, you assume like pure Yang-Mills, like without charge matter. And precisely when you have 16 supercharges, it's still true that even if you have charge matter, you can still fully determine the theory at a regular point just by specifying the rank of the gauge group and the gauge coupling, right? So maybe the fact that you are just thinking that these are the two things that you can vary, just the rank and the gauge coupling, is what makes you recover only the result that you get with 16 supercharges. And if we reduce the level of supersymmetry, then it would be important that you add in the ansat the charge matter. I don't know. These are so have you thought about it, or I don't know?
Yeah, I haven't thought in great detail. I mean, one comment I can make, maybe you could tell me, is, for example, you don't get I mean, the constraints actually get stronger, but nonetheless, for example, you don't get agreement between SON and SUN anymore when you're not at this maximum value of the coupling. So I was wondering if like supersymmetry fixed this relationship between the coupling, the Yang-Mills coupling and the gravitational coupling. This value here, this like G Yang-Mills squared is twice the ratio of the string scale and the Planck scale squared. That's the only value of the coupling at which this plot agrees for SON and for SUN. So maybe supersymmetry is secretly in the fact that that coupling is fixed to that value. And then, yeah, otherwise, well, I didn't understand exactly what you meant with the charged matter, since that's not here, but.
Yeah, I was wondering, like, yeah, how your analysis would change if in the answer for scattering, you add the charge matter contribution, and that maybe it becomes important precisely when you have less supersymmetry, because then the theory is not fully determined by the rank of the gauge group. While with 16 supercharges, even if you have charge matter, still that's constrained, like because of the level of supersymmetry, right? You can fully determine the theory just by saying the rank of the gauge group at a regular point. So maybe, I don't know, it's a good answer in that case, but not in general if you have less supersymmetry.
Yeah. Well, if you add charge matter, I mean, it will only get more constrained. Like if you just put charged fundamentals, you know, whatever fermions or scalars, then, you know, they'll still have some G Yang-Mills squared in the amplitude, and that's, you know,
Do you think that these constraints remain or even become stronger if you are charged matter, or what's the expectation?
I think they'll have to be stronger because the amplitude we care about will just be a special case. Well, no, but sorry. If you add charged matter though, that will only appear at one loop. So I don't
I think the constraint you find are general in the sense that it's true that you can get much bigger rank gauge groups, but there would be effective gauge fields like in 4 dimensions or something, and the amplitudes for those would grow. They would not be bounded. They would violate unitarity, as in they would have very large S. And you are demanding to have a unitary amplitude. So in string theory, what would happen is that you would eventually, to unitarize it, you would have to reach string scale physics, which would be effectively reintroduce supersymmetry and all the constraints that you have for string theory. So I would imagine that what you find is general in the sense that if you ask for an amplitude which is unitary at arbitrarily large S, then probably you must then have a string theory and all these things. And I think what Irene was saying, that you can have much bigger gauge groups. That's true, but you would not have a unitary amplitude for those theories. It would grow with with big powers of S, because
right, okay.
I think what you find is general, but you could have effectively much bigger rank gauge groups, but they would not have a unitary amplitude by themselves. By the time you reach the energy scale where it begins to unitarize, I think you would have supersymmetry and everything again, because
you're thinking just of open string, Aaron, or also within?
No, even closed strings as well. Yeah, I think. I mean, if you just take a low energy theory with SU 56 or something, and then you calculate the scattering, I think they will not, because you will not have the string states yet. So they would just grow like some S squared or something. And then if you want to unitarize, you have to go to some S where you reach the string scale. And then I would imagine then, you essentially going back to some string theory. That's just my thing, but I think we should finish soon. So I should not, yeah. That's just my thinking.
Yeah. Yeah, well, but also without gravity, it's a lot of this, both the problem, but then also the constraints on the solution have very much to do with gravity here, because I mean, you could have a well-behaved amplitude without gravity, without it being stringy. But once you introduce gravity, it needs to be unitarized somehow. It looks like these stringy amplitudes are the only examples that we know of, and it's actually, as I tried to argue, they're kind of naturally motivated when you look at this infinite product way. And then, so that's just motivating this arena of this gravitational arena, which is the arena that's sort of at first order most interesting. You can work at tree level and it's interesting. But if you take gravity away and then you want to start asking questions, much more open. And I'll comment on it again at the end, kind of why it's easy to see why that's the case. So these are the constraints. These different pieces of the curve come in at mass level 1. The strongest constraints here are at mass level 2, and then finally in the vicinity of 10D, it's mass level 3. And you get these sort of more complicated looking constraints. And what's very interesting is that once you fix the coupling, as I was saying before, to be this factor is equal to 2, which was the max value, or yeah, I write that here. Then for the positivity bounds, for example, for the first mass level, look like this. So they're not the same function. So they're not even the same function, but they end up sharing the same common factor that actually enforces positivity, right? So these factors are the same, and these are the ones that actually enforce positivity. So it's very non-trivial that it just spits out and produces the same function of rank. Not even the same function, but the same factor. So I thought that was very interesting. And hinting at, and indeed, is there supersymmetry behind the scenes that has to do with this? That's unclear, and something I've only thought a little bit about, but would definitely like to interrogate further. So lastly,
just we're already running out of time.
Oh yeah, we can move on then.
It's partially our fault because we are asking many questions, but yeah, if you can.
Yeah, I have one slide really, or two slides. I mean,
thank you.
So yeah, I'll just go quickly then. So we don't need to, since you guys are used to the game by now. Okay, so the same game, we just write the Higgs amplitude, multiply it by the stringy factor. Okay, and just constrain. I mean, these are the gauge couplings in the standard model, and this is the Higgs quartic. Okay. So we get this plot if we again use gut scale couplings. So this is the Higgs quartic versus the ratio of the string scale and the Planck scale. So this gray dashed line is, maybe some of you know, when you just do the standard model and nothing else, and you run the Higgs quartic coupling to high energy at around 10 to the 10 GeV, the Higgs coupling goes negative. And it stays with, this is about like I think 3 sigma bound on what the Higgs coupling is in the neighborhood of the gut scale. Okay, and so in the stringy ansatz, it's funny. It's not symmetric between the two sides, and it really has this steep bound on the negative Higgs quartic side. Okay, the side that produces a vacuum instability. So I thought that was it's kind of amusing. And again, and just an example of something that's not totally open-ended. These ansatzes are surprisingly constrained. So just a comment related to the questions I've been getting. If you do the open stringy version, since people are interested. So let's say you do the open stringy version at tree level. Let's say without gravity, just analyze the 4 gluon amplitude. Okay, we know this is from open string theory, this is what you get. You can actually even do this for the nonlinear sigma model if you do the Lovelace-Shapiro version, which has like 1/2 here and a 1/2 here. You get no interesting constraints at tree level. So gravity was really important for sort of producing these singlets, these kinds of subleading Reggie states that subleading Reggie trajectories that produced these non-trivial constraints. So it's sort of observational, but that's the observation, is that gravity was really crucial. And it'd be interesting to understand more from this sort of analyticity, amplitude side, but also from the swampland side, why that might be. So in the open string case, you don't get anything at tree level. Yeah, so we looked at completions of massless amplitudes. In these closed stringy versions, you get interesting constraints. Graviton exchange is crucial. And future directions would be deforming the stringy prefactor, these sort of Kuhn amplitude ideas, generalizations thereof. Do these statements hold in the dispersive representations? And then can we do open stringy ansatz? You get gravity from the annulus when you have a weakly coupled open string. So can you construct sensible ansatzes that include the annulus? So it's a harder game to play technically, but perhaps could furnish some really interesting constraints as well. So yeah, I'll stop there.